Hey everyone, Mr. Fransky here, coming back with another video. Today we're going to be talking about derivatives of inverse functions just in general. We've already talked about derivatives of trig inverse functions specifically, but today we're going to be able to find the derivative of an inverse function at a buddy point by using a function's derivative graphically, algebraically, and also using a table. So buddy points sometimes are also called corresponding points in some textbooks. So let's take a look. So key vocabulary today: chain rule, which we've been doing lots of, inverse function, which we know a little bit about, and then buddy points we'll learn about as well. So first we're going to do some practice warm-up problems here. So we've been talking about inverse trig. If you want to pause the video and give these a shot, feel free. We'll come back and do them together. All right, let's give these a shot. So we're looking for the equation of the tangent line, so we need a point and a slope. So our point here, our x-coordinate's -2, and then secant inverse of -2. So to think about that, I'm thinking, okay, well, secant inverse, that's 1 over cosine. So I'm going to be somewhere on the top of the circle, and cosine I need to be then -1/2. So that's going to happen right here. That's where secant is -2 and cosine is -1/2. That looks like 2 pi over 3. And then our slope is going to be the derivative of this guy. So derivative of secant is 1 over absolute value of x times the square root of x squared minus 1. And we're going to evaluate that at x equals -2. So that's going to be 1 over 2 times the square root of 4 minus 1, which is 3. And I'm just going to leave the slope like that, because why bother messing with it? So we're going to have y minus 2 pi over 3 equal to our slope, which is 1 over 2 root 3 times x plus 2. And there's the equation for our tangent line. Not too bad. Next up, particle follows the position function x of t equals cotangent inverse 1 over root t. They want v of -√3. All right, so our point is going to be, if we plug -√3 in here, let's see. That's a messy one. Let's see. So am I missing something? Let's see, it would be cotangent inverse of 1 over square root of -√3. Oh, I don't have to find the tangent line. That's why this is messing me up. Come on, Mr. Fransky. All right, so then what? Just v. So that's just x prime. So v of t is x prime of t, which in this case is going to be -1 over 1 plus this baby function squared, so 1 over root t squared, multiplied by the derivative of the inside function. This is t to the -1/2. So I'm going to move that to the front, -1/2, t to the -3/2. Okay, so now we're going to plug this in everywhere, but first let's make this a little prettier. So that's -1 over 1 plus 1 over t. Times, this would be -1 over 2t to the 3/2. Ugh, that is not beautiful. But we're going to evaluate that at t equals -√3. So that's going to be -1 over 1 plus -1 over root 3, multiplied by -1 over, let's see, 2 times -√3 to the 3/2. I am starting to doubt this example a little bit. That is the correct math, but taking the square root, right, this 2 down here means square root of a negative number, is not so great. So hopefully we got this answer, but I would have a domain question on this problem. All right, always good to think about that. All right, moving on. So a little bit of inverse functions. So inverse functions, remember what I always say is inverse functions undo each other. They undo each other. And basically what that means is if you plug a value into a function and then you take the result and you plug it into its inverse, remember these old function machines? Okay, so if you take a value, you plug it into some function f of x, and then you take the result, which is going to be some y value, and plug it right into the inverse, it should give you back out x. Okay, so f somehow scrambles x up, and then f inverse unscrambles the x. And you probably have seen this graphically somewhere before, where you have a graph, maybe like e to the x. E to the x is an easy one to do the inverse of. Okay, so we have e to the x. Then you may have seen you can reflect it over the line y equals x, and it gives you the inverse function. And that is hopefully a function that you recognize as natural log of x. You can do this with any graph, though. If you have like a line, so say you have a line that has like a slope of 2 through the point right here, I don't know. Okay, if you reflect that over the line y equals x, the inverse function is going to look something like this. Okay, so all you're really doing is you're flipping it over the line y equals x, and that will give you the inverse function. Algebraically, like we said, whatever y value comes out, you have to be able to plug it in and get back out x. So often what you hear is if you want to find the inverse, all you have to do is switch the x and y. So let's say, for example, I have y equals x squared, and I want the inverse function, so f inverse of x. Okay, so you switch x and y, x equals y squared, and then you solve for y. So y would be square root of x. Now this is kind of weird because you have to have a plus or minus, but if we want it to be a function, we would just do square root of x. And then you can check, right? So if like I want to find f of 3, that would be 3 squared, which is 9. And then if I do f inverse of 3, or f inverse of 9, excuse me, so I take the result, plug it into f inverse, that would be root 9, which is 3. So we started with 3, the function scrambled it up, and then the inverse undoes it, okay, because inverse functions undo each other. So that's kind of where the point-by-point thing is. If AB is on f of x, then what point would be on the inverse? Well, if A is sent to B, B must be sent then back to A by the inverse. Then BA is on the inverse. And this is what I call the buddy point. So this right here is called the buddy point. These 2 points are buddies because there are important properties that these 2 points share. So if xy is on the function, then yx is going to be on the inverse. And we can see that like maybe with this function right here. So like maybe this is like 1, 4. Then the point 4, 1, which is directly across the one y equals x, is going to be on the inverse. Not too bad. Okay, so algebraically switch x and y, graphically switch over the line y equals x, and point by point just means AB is on f, that means BA is going to be on the inverse. All right, so I want to see here just some specific functions that do undo each other. So if we have y equals 2x plus 1, let's find the f inverse. Okay, so we're going to find the inverse of x. We switch x and y. X is 2y plus 1. And now we are going to solve for y. So we have x minus 1 over 2 equals y. And that is our f inverse, x minus 1 over 2. Now, we should be able to do composition of these functions, and they should undo each other always. So if I do f of f inverse of x, I'm only going to go one direction here. In pre-calc, you probably had to go both directions. But f of f inverse is going to be 2 times x minus 1 over 2 plus 1. So I plugged the f inverse function into this little x right here. I just put it inside. 2's cancel, 1's cancel, it is indeed x. So that proves that they always undo each other. F of x equals e to the x. E to the x looks something like this. And if we have y equals e to the x, and we switch x and y, we have x equals e to the y. We kind of have to think about this, but to undo an exponent, remember we use logs. So we do natural log of both sides. So our natural log of x, natural log of e to the y, a couple ways you can do this. One is you can just say, well, natural log is asking, what power do I have to take e to make e to the y? Well, that answer is y. The other way you can do it is put the y to the front. Remember our log rules, y ln e, and ln e is 1. So either way, we have y equals ln x. So that is our inverse function here. Looks like that. Okay. And if you put the functions into each other, so f inverse is ln x. You put the functions into each other, if you do f of f inverse of x again, you get, so it would be e to the power ln x. If you go the other way, you get ln of e to the x. And either way, you end up with x. Okay, so they undo each other. Now, if we were to graph this guy over here, 2x plus 1, that's exactly what we had in the last slide, actually. So 2x plus 1, reflect over the line y equals x. This should give us 1 half x minus 1 half. So it's going to look something like that. Add by that. Y-intercept of 1 half, slope of 1 half, sure. So let's look at the slopes, because that's really what we're interested in so far in calculus is these derivatives. I want to know, how does the derivative compare? Well, let's look at the slopes of these two. So slope of f over here was 2. Slope over here was 1 half. Interesting. So it looks like they might be reciprocals, maybe. Over here we have, if we look at any point, so like maybe right here, so slope there is pretty steep. So the same x value, doesn't look like there's really any relationship there, but if I reflect over the line y equals x to its buddy point, it looks like those slopes also might be reciprocals of each other. Interesting. So our hypothesis is that f of x and f inverse of x somehow must have reciprocal slopes. But I was bringing it up over here, and I did a bad job of drawing it. Let me see if I can do better. So if I know the slope right here, that x value doesn't even have a value over here. And same thing right here. If I know the slope right here, down here the slope is very, very steep. Those don't look like they're related very much. But if I look at like the slope at 0 for this guy, and then I look at the slope over here, it looks like those two might be reciprocals of each other, which makes sense to me because it's reflected over that line y equals x. So those slopes look like they could maybe be reciprocals of each other somehow. So it's only at buddy points. Buddy points. Oh, come on, right. Okay, so that is kind of what we're thinking about, is the slopes might somehow be reciprocals of each other. So let's see if we can prove it. So this is definitely a proof at proof. You don't have to know this, but the punchline, which we're going to get to next, is what you're going to have to know. So what I have is if g of x is equal to f inverse of x. What I want is a formula for g prime of x. So I want to know what is the derivative of f inverse, and is it somehow related to f? Well, using this idea, if I take f of both sides, then I have f of g of x is equal to x, right? Because f of f inverse, these are inverse functions, they undo each other. Now what I'm going to do is take the derivative of both sides. The right side is easy, it's 1. The left side, this is exactly chain rule, right? It's f prime at g of x multiplied by g prime of x. Well, that's useful because I want g prime of x, so we can solve for it. So g prime of x is equal to 1 over f prime evaluated at g of x. So what does this mean? So there is some kind of a reciprocal going on here. The derivative of g is the reciprocal of the derivative of f, but it's evaluated at the y value of the g function. Right? Because if I take x and I plug it into g, that's going to give me out a y value. So what this tells me is if ab is on f of x, and f prime of x, f prime of a, let's say, is equal to m. So if ab is on f of x and the derivative of a is equal to m, that means that ba is on g of x, which is our inverse function. And I can't say anything about g prime of a, but I can say something about g prime of b. So see, this is what I was talking about with the buddy points. It's important to look at the x-coordinate that corresponds to the y-coordinate of the f function. And that's going to be equal to 1 over m. So g prime of b is going to be 1 over f prime at the a value, which is the y-coordinate of the g function. This is kind of the bread and butter. And this is what our punchline is that I want to talk about. So the punchline is if ab is on f of x, and f prime of a is equal to m, then ba is on g of x, and g prime of b is equal to 1 over m. So it's all about these buddy points. So like if I were to graph, let's just graph the right side of a parabola, x squared, and then we'll graph root x. Okay, so at like, let's say 4. Okay, so the point 416 is up here. And the slope there is going to be very steep, right? It's going to be a slope of 8 because we have 2x. So the slope there would be 8. The slope at 4 is not 1/8, but the slope out at 16, right? The point 16,4 is on here. That's the corresponding point, or the buddy point. The slope there is going to be the reciprocal. There the slope is going to be 1/8. Here it's 8. I should write that better. So 2x evaluated at x equals 4 would be 8. So then the slope at the buddy point is 1/8. All right, let's see what we can say about this. So if the point 3,4 is on f of x and f prime of 3 is 5, the question is what can we say about the inverse? So I would suggest writing this out every time. 3,4 is on f and f prime of 3 is 5. Then what does that mean about f inverse? Well, I know 4,3 is on it, on f inverse, and f inverse this is kind of weird, f inverse prime of 4. So not of 3, of 4 is 1/5. So it's always using that buddy point. So it's the y-coordinate of the f function will be the x-coordinate of the inverse, and we can talk about them very reciprocals at that buddy point. So in the next video, I'm going to do the problems that you have on your worksheet for 3.8b, and we're going to be able to do a lot more practice with these inverse functions. Hope you learned something here. I'll talk to you in the next video.